Kobe. It's my pleasure to introduce our second invited speaker of this conference, Yosuke Todo. So Yosuke is a distinguished researcher at NTT. And before this, he studied here actually in Kobe, where he obtained in 2017 his PhD from the Kobe University. During his PhD, he invented the division property that you have already, most of you heard about. It's a very powerful technique to search for integral distinguishers. So this, in particular, this technique permitted him to break the cipher, block cipher MISTY-1, a very old and well-known cipher, and breaking it was an open problem for many years. And this work gave him the Best Paper Award at Crypto 2015. So Yosuke worked also in other types of cryptanalysis. Well, he has very, very nice results published at the best conferences of our domain. Is surely one of the most brilliant and talented cryptanalysts of his generation. And so it's our pleasure to have Yosuke with us today that will tell us a story behind the invention of the division property.
Okay, so thank you very much for introduction. So I'm Yosuke Todo at the NTT Social Informatics Laboratories. So first of all, I would like to thank program coaches and so also the all editorial board members. So thank you very much for inviting me. So I'm very pleased to give the invited talk at this nice conference. So today I want to talk the story behind developing the division property. So it doesn't work. Okay, it works. Okay, so the topic is about division property. So the division property was initially proposed at Eurocrypt 2015. And so this is a tool to find the integral distinguishers regionally. And so as introductions by Boris, so very soon after, so at Crypto 2050, so this technique can be used to break the full MISTY-1. So I think it's my fortune, maybe. So this paper got the best paper award at Crypto 2050, and many researchers recognize these techniques. And after that, many papers, many authors, many researchers have focused on these topics and published many follow-up works. So actually, this is the last day. So I count the number of papers in the IACR conference, so the Crypto, Eurocrypt, Asia Crypto, and FSE. And I just count the number of papers highly related to the division property. So I found almost 30 papers. So from the 2050. So one is foundations for more mathematical something. So and another one is MIRP or SAT SMT based automatic search tool. And also the extension to the cube attack. And sometimes, so like breaking the MISTY-1. So it gets best key recovery attack against some important ciphers. So now here is FSE. So I think many nice geometric cryptographers joined this conference. So here, so I want to thank all the contributors for enhancing the division property. So today, so I don't talk the latest result. So just past, I only talk the past story. So beginning story, so when I developed the division property. So because I think as I'm no longer as a proper person who speaks the latest result, maybe as a many researcher already knows the latest result. So I think today I want to talk the topic only I can talk. So this is a story from the 2012 to 2050. But of course, before the talk, so I need to explain the brief introduction of the division property. So because someone doesn't know this technique. Okay, so the topic is about integral attack, so also known as the square attack. So the target is AES, So now, AES state consists of 16 bytes. So, and with this matrix structures. So now we prepare the 2 to the 8 chosen plain text. So it means this red byte takes all value. And white byte is a constant. So now we apply sub-byte. Of course, sub-byte S-box is a permutations. So this property can be preserved. And next apply the shift rows, but so first row is identity map, so it's exactly the same. And next, mixed columns. So the mixed column is a linear layer, and this 1 byte active goes to the 4 byte active in these columns. So it means we focus on 1 byte of the red byte, so it takes all value from 0 to 0xFF. And white bytes are constant. Okay, this is the 1 round properties. Then next 2 rounds, sub byte is the same, and the shift row goes to the change the active positions. And mixed columns, we have this structure. It means if we pick 1 byte from the 16 bytes, it takes all value. Okay. Then next, sub byte shift rows, so that we keep the same property. After that, in the mixed columns, we no longer observe all properties, but mixed column is linear. So the sum of the value is 0. So this property is preserved, and we call this property balance property. And so now we get 3-round integral square distinguishers. So it's a powerful attack tool against AES. And also, we can extend this attack with 4-round distinguishers by using these methods, higher order integral techniques. So we have focused on these diagonals, and we activate the 4 bytes at the same time, so that we use the 2 to the 32 chosen plain text. Then 1 round encryptions, we have these structures, but this structure means we have 2 to the 24 structures, and each structure has this form. So as a result, so we have a 4-round integral distinguisher. So when I explain the division property, I sometimes use this slide. So AES, maybe so when we consider the AES, so that we have integral property can get the 4-round integral distinguishers, but we also have very similar results. So the degree estimation. So when we estimate the algebraic degree, then we have some result. But so even if we use some nice so the upper bound of the degree estimations, so we can't get the same result. So usually the integral property is better than degree estimation in that case. But okay, so now we exchange the S-box. So originally AES box is the algebraic degree 7, but now so that we modify the S-box, and we choose a very weak S-box whose degree is only algebraic degree 3. Then what happens is that in degree estimation, we can get more nice results than integral property. So at that case, degree estimation is better than integral property. So actually, this is a very interesting situation, because now we have integral attack, and also higher order differential attack comes from the degree estimation. So I think both attacks are the same, because we first prepare the set of the chosen plain text and compute the set of the ciphertext, and focus on the sum of the ciphertext. And if this sum is 0 or not, so this is the distinguisher on the integral and the high order differential attack. So these two attacks has the same interface, but different result. So this is the main motivations why division property is important. So initially, my motivation is we take the best of 2 methods. So for example, the integral property, so that in the S-box is a permutation. So if input takes all value, of course, output takes all value. If the input is a balanced property, balance means the sum of the this value is 0, and so that it's unknown. But integral property overlooks this property. So now S box is the degree D. So if we activate the D plus 1 bit active, then the output is balanced because of the degree estimation. So, but integral properties overlooked this one. So this is the interesting point. So that we want to, if we can use the degree, algebraic degree at the same time with integral property, there is a possibility we can improve something. So this is the idea. So of the division property. Originally, X is a set of chosen plain text. And so the Y is the set of the ciphertext. And we want to focus on the sum of the Y to the EI. If the EI is a unit vector. So if we focus on the ith bit of the ciphertext, so we want to know this value is 0 or not for all key. But if we want to compute this, if we want to get this distinguishes in experimentally, for example, it's practically impossible because the set of the X is too many and the number of key is also too many, so it's practically impossible. So now in the division property, we change the set of X to the set of the K. So it's a some single basis transformations. So originally this is a set X, but we use a set of the U such that the sum of the X to the U is non-zero. So, and we also have the same property of the set of the K of the ciphertext side. And if the unit vector EI is, and we check the unit vector EI is included in the KR or not. If it's not included, so from the definitions, we can say the sum of the EX to the EI is always 0. So we need all elements in Y, but there are, I think it's maybe originally so from the left side, so that we need all elements in Y. But of course, there are too many elements, so it's practically impossible to compute it. But after basis transformation from X to K, so the partial information, because the KR is too many elements, KR includes too many elements, but only the focus is a unit vector is included or not. So this partial information of KR is enough. So it's one of the reason the left side is practically impossible, but the right side is possible. And so after that, so the 2060 FSE. So I introduced the 3 subset variants so that we use the K set, L set like this. And the K set is now the sum of the X to the U is the polynomial of the key. And L set is the sum of the X to the U is equal to the 1. And so we get the same, and the goal is the same. Okay, so after proposal, so we have so related works about the L set. So I initially thought so K set is enough, and maybe if we use the L set, so it's a bit difficult to evaluate the propagations in practice. And K set is much simpler, and so it's practically possible to compute the propagation. So I mainly focus on the K set. But so after the proposal and many follow-up works, and by using the MIRP tool, and nowadays L set propagation is more common, and we have a different name. So the one is a parity set. So it's a Crypto 2060. So this is very similar to the L set, and it provides a beneficial mathematical view. And also Asia Crypto 2020, so the monomial prediction. So this is also the equivalent with the L set propagations, and monomial trail and monomial har is propagation of the L set. So I think as a K set and L set is a meaningless word. So it's so just the alphabet. So I think so this type of terminology is much reflected to the meaning. So direct wording. So at that case, so I think using this type of word is better. Okay, so up to here. So from here, so I want to go back to the 10 years ago. So and let's start the main story. Okay, so what was the first step? So 2012, so almost 10 years ago. So I joined the symmetric research group at NTT corporations. So in this group, so there are three symmetric cryptographers in our group. So one is Kazumaro Aoki. So now he sits here. So he is a subgroup leader of our research group. And another person is Kan Yasuda. So that he is a probable security expert. And maybe as the last one is a very famous researcher, Yu Sasaki. So he is a teacher for me. Okay, so when I entered this group, so I'm not so familiar with symmetric cryptanalysis, actually, because I don't know the differential cryptanalysis, linear cryptanalysis, of course, integral cryptanalysis. So my colleagues say, okay, so you study everything. So I experiment. So my approach is I experimentally verify the famous cryptanalysis to understand them very well. So, okay, so I first read the differential cryptanalysis paper and I implement it. And next, okay, so look at the linear cryptanalysis paper and implement it and like this. So during this process, so I was interested in the integral attack. So my first experiment is like this. So FSE cipher, very easy to understand. So now I first implement the FSE cipher with random permutations. So a function is generated at random, and we check the integral distinguisher experimentally. So in the integral attack, we use all balance constant. So like this. Okay, so first left branch is a constant. Then what happens? This blue line is fixed to constant. And we activate the right branch. So we take all value in the right branch. Then what happens? So like this. So this red line takes all values. So in the 3 round, you can see exclusive OR with 2 odd values. What happens is that it's the same as the integral square attack on the AES. It's a balanced. So as a result, we get 4-round integral distinguisher. So it's a very simple and but powerful, so and easy to understand. So maybe everyone understands this attack. Yeah. So I first implement this distinguisher, this cipher, and I experimentally verify this distinguisher. Next focus is a generalized FSE. So now I change the structure of the FSE to the generalized FSE, and similarly to the FSE, I experimentally check integral distinguisher against the generalized FSE. So now here the C means a constant, and only the most right branch takes the odd value. Okay, we do the same. Okay, so this blue line is a constant, so it's a totally fixed. And this red line is all values. Okay, so similarly to the FSE in the 1, 2, or so the 1, 2, 3, 4 round and 5 rounds. So we have exclusive OR with 2 all values. So what happens? So that this value becomes balanced. So this path is a bit meaningless, but here, okay, so that we have 6 rounds, 1, 2, 3, 4, 5, 6, yes. So we have 6-round integral distinguisher using 2 to the B. B means size of the branch. So 2 to the B chosen plain text. Okay, so then now we want to extend this idea to higher order integral. So this similarly to the higher order integral attack on AES. So now we add 2 rounds to the beginning of the integral 6-round integral distinguishers. And all goes to blah, 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 like this. So the structure is CAAA. Where the AAA means even if we concatenate these 3 values, it has OR property. So Now, if we have 2 to the 3b chosen plain text, so after 2 rounds, we can get 2 to the 2b set, where each set take CCCA. So it's the input of the 6th round integral distributions. So after 2 plus 6 rounds, the sum is always 0. So as a result, we get 8 round integral distinguishes by using 2 to the 3b chosen plain text. So of course, it's also simple, and maybe you understand very well, I think. Okay, so what I did in there. So I prepare the FSE and the GFN with several parameters, so that I change the size of the bit of the F functions, and I change the number of the branch, and I check each integral distinguish experimentally. Sometimes I observed very strange distinguishes. So strange means I can't prove this distinguisher by using integral property. So this is an example. So now here is a type 2 generalized FSE, but a function is like this. So not so random permutations. We first apply 2 S boxes in parallel, and the linear layer is applied. So of course, this is one class of the type 2 generalized FSE. So similarly to the random permutation case, we have 6 round integral distinguishers by activating the last branch. So of course, it's the same. But surprisingly, then the size of the S box is 4. We observe the balance property in this branch. And when the size of the S box is 5, we can't observe balance anymore. So this is first questions for me. So when I developed the division property. So originally, I thought the integral property is a very nice and very powerful tool, and everything I can prove it. But now we had something strange one, so that we can't prove the integral property. But this is not new fund. It's very interesting. So I survey several kinds of paper, not only English one, but also Japanese one. I found very nice papers. So this one, maybe you can't understand. So it's a 一般化フェイステル構造の飽和特性. It's in Japanese. So it's a saturation characteristics of generalized facial structure. So the Tsuno-san is very famous researcher in Japan. So he develops, he analyzed several kinds of the integral distinguishes. And in his Japanese article, I found very, very similar property. So they showed very related conjectures and strange integral distinction on Creffier. So Creffier was selected at the test of time awards yesterday. So he presents very nice integral distinguisher, very strange, and so that not easy to verify integral distinguishers. So assuming this conjecture holds, we can prove this strange behavior. So what he did. So this is the Tsuno conjecture. So he presents LK model. LK model is defined like this. So x1, x2, blah, 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 xk is the input. And now, so this xi is applied to the balanced function gi. And balanced function is defined like this. And compute the sum. And output is a y. Okay. So he defined this LK model. And in Tsuno's conjecture, say if L is equal to 2k, the number of appearance such that y is equal to b is equal to the number of appearance, the y equals 0 mod 2. And if L is less than 2k, the number of appearance y is equal to b is equal to 0 mod 2. Okay, so what I say. So this is the image figure, so the mod 2 or property. So we call this property mod 2 or, but sometimes we call this property even or odd property in the integral cryptanalysis. But so I called this property mod 2 or during my research. So mod 2 or is like this. Okay, so now this is a case of the L is 4. So we focus on the number of appearance y. So the 0 appear. So the number of appearance of 0 is 30 and 50, 50, 21, blah, blah, blah. So you notice all case, the number of appearance is odd. So then if we compute the mod 2 or, it's equivalent with odd. And so if we apply the additional S box here, so mod 2 or property is perfectly preserved. Okay, so now we review the type 2 generalized FSE, so from the Tsuno's conjecture. So now CCCAA. Okay, so now here is x1, x2, and here is y1, y2. So this function is like this. S1, S2, L1 is F3, and S3, S4, L2 is F8. And so the y1, y2 is computed like this. But linear function can be decomposed. So we can rewrite this function like this. So now, in my experiments, we use 4-bit S box, and the number of the input is 2. So it means L is equal to 2k. So this case. So we know y1, y2 has a property mod 2 or. So this pink line is a mod 2 or, and as I say, mod 2 or can propagate through the nonlinear functions. So here is mod 2 or, and here all property is XORed with mod 2 or. So now here is balanced. So thanks to the Tsuno's conjecture, we can prove this property. But so I say it's a conjecture. So yes, this is a conjecture, so not the proof. Because they, in his Japanese paper, they didn't prove LK model. They only prove 4K model. So if the size of the S box is a 4, they provide proof. So their proof is enough to explain my small experiments. So because my small experiments use the 4-bit S boxes. But not enough for Crefia, because Crefia use 8-bit S boxes. So he did several kinds of many experiments, and so experimentally showed H4 model is valid. But of course, in general, so there are no proof about the LK model. So this is the conjecture. This is the first step of the division property. So I first noticed this conjecture. So my first work, how to prove this conjecture. So I think, so this proof is the first step of the division property. So of course, so the Tsuno's conjecture is very specialized structure. So the first we apply the balance function and the sum, and that's all. So more complicated functions, we no longer apply it. But this proof is not so general like division property. But nowadays, so that I review this Tsuno's conjectures, and we wanted to prove these conjectures by using the division property. It's trivial. Okay, so now we want to understand, we want to beyond the Tsuno's conjectures. Okay, so originally we have CCAA, and so by combining higher order integral attack and the Tsuno's property, Then we observe a balance property here. So now all, and so after one round, this is a CCCA. Then to know the property, we get balance here. Yep. However, very interesting one. So the experimentally again, I did this experiment, and as a result, if this F function consists of 4-bit S boxes and linear layer, surprisingly, we observed balance property more one round. Why? So unfortunately, so that it's not possible to prove this property by using the Tsunoda's property. So we need more general theory to understand this phenomenon. So how to generalize Tsunoda's property? So this is my next step. So we expect a similar phenomenon to the Tsunoda's property in more complicated functions. So the Tsunoda's property will only focus on the balance function, the sum, but maybe we have a more complicated case, and maybe we have the similar result, but we don't know. So my approach, maybe understanding model 2 is very important. But unfortunately, the FSE is too complicated, so it's not unlike SPN. So the input data comes from the so this branch comes from the identity like, and so it's very complicated to understand the property of the FSE. So let's go to the SPN. Okay, so we first give up the FSE, and we next go to the SPN, because SPN is much simpler and to understand. Yeah. So this is my next experiment on the SPN structure. So 4-bit S boxes and then linear layer. Okay, so my experiments first. So we have this 1, 2, 3 branch takes all values. So we use the 2 to the 12 chosen plain text. So 4, 8, 12. And the last branch is fixed to constant. So if we use the integral property only, then the distinguisher is up to 2 rounds always, independent of the S box and linear layer. But of course, so there is a possibility of the higher order differential attack. But if we only use the integral property, up to 2 rounds. But so the experimentally, I observed 3-round integral distinguishers. And very interesting one is the 1 round before of the 3 rounds. So the 2-round output takes model 2 all. So I think, okay, so the SPN is also interesting. So I try to several kinds of the experiments for the SPN. So I define NL model so that it's use N L-bit S boxes and repeats the number of rounds. And I experimentally check how many number of rounds can we observe the integral distinguisher. So this is the case when we use 4-bit S boxes. So N is the number of S boxes in 1 round, and active, it means the number of active S boxes. So up to here, so it's a 2-round integral distinguisher. So it's exactly the same as the integral propagation of the integral property. But from here, so we observe something strange property in the context of integral property. So here we observe 3-round integral distinguishers, and moreover, if we have 6 S boxes, 6 4-bit S boxes, we have 4-round integral distinguisher. So I initially thought, oh, it's very nice result because I only know integral property. I didn't know the higher order differential attack. So when I did this research, so 3-round integral distinguisher, it's very nice because I thought it's a non-trivial distinguisher. But very soon my colleague will say, you overlook the degree estimations. higher order differential attack. So I was super surprised. So because I didn't know the higher order differential attack, so when I did this research, and so I read the higher order differential papers, and so at that time I understand what is algebraic degree, algebraic normal form. So before that, I didn't know about the degree and Boolean functions anymore. So, but I first read the essential, so the first paper was the higher order differential attack. So I didn't know the advanced method to estimate the algebraic degree. So I first think, okay, but it's a no problem because we observe 4-round integral distinguisher too. 3-round distinguisher, yes, we can prove it by using the degree estimations. So simple the algebraic degree bound, but 4-round, so 3 times 3 times 3 is 27, but it's larger than 20. Okay, no problem, because 4-round integral distinguisher is new. But it's my mistake, because I didn't know this nice paper, FSE 2011. So that we have a nice so the upper bound papers of the algebraic degree for the SPN structure. So if we use this technique, we can prove 4-round integral distinguishers, but at that time I hadn't recognized it. So I want to prove my method. So my view always comes from the integral property. So integral property like analysis. So now here is the SPN structure, so the all constant. Okay, so after 1 round, or, I don't know. And so the next 1 round, mod 2 or mod 2 or mod 2 or mod 2 or mod 2 or. And so the next round, balance. One question is, so that when we use the integral property, we have many A. Here is A, here is A, here is A. Everything is A. So it's super complicated. So we have many A, but each A is a different property, I think. So the question is how to distinguish these different kinds of the A. So now let's understand what is a mod 2 all. So now here is all property. All property is very nice, so that because very beautiful. So that from the 0 to F, so that it appears only at once. Now, so that we use higher order integral. It's a 1 branch of the AA, so then it's also beautiful. So the number of appearance of the 0 is 16 and 63. So it's very beautiful. But in mod 2 all, not so, like this. So yeah, so if we say all property, but everything is different. It's all, but it's different property. So we need to distinguish them. So mod 2 all is very similar to A or AA. So this property is preserved even if a permutation is applied, but different. How to distinguish it? So this is the next step. So my approach is like this. So first, originally, so that we focus on this branch, 4-bit values. So now we have additional 1 bit from the different branch. And we check the number of frequencies of the 5-bit value, not 4-bit. Then this nice all property, then we again observe nice property. 0 appears 8 times. And so now we have additional 1 bit from the top branch. So we have 1F. So the number of appearance of 1F is also 8. So it's very beautiful. But in mod 2 all is not so. If we involve additional 1 bit from the top, and in total we focus on the 5-bit, then it's not, we no longer observe mod 2 all. Okay, so from this observation, so that we need to change our thought. Originally, so that in the integral property, we focus on the property of each branch. So we focus on this branch, and this branch is all or balance or constant or even or mod to all. But it's not enough. So instead, my focus is by what side do we keep the mod to all? So this is the experimental result on the SPN in the context of the mod to all. So now here is L, here is all, and here is the CAA means so we use the 2 to the 8 input. So in total, 2 to the 23 input we use. Okay, so now we extract 23 bit from the bottom. It's a mod to all. Mod to all, it's a all, exactly all. Okay, so now we apply one round. What happens? As a result, up to 21-bit extraction, it has mod to all. But if we extract 22-bit, we no longer observe mod to all. And similarly, 50-bit extraction, mod to all, 5-bit extraction, mod to all, 2-bit extraction, mod to all. And 2-bit extraction, mod to all is equal to the balanced. So from now, we first think about the algebraic structure. Okay, so now we have k-bit extraction has mod to all in the input, and we apply the Boolean function f, vectorial Boolean function f. And now here is algebraic normal form. The question is, how many bits of extraction do we have mod to all in the output? So now, here is the algebraic normal form, and so we want to focus on the sum of the x over the fx, and it's like this. And so we can change the positions, and this part is fixed. So we can't control anything because it's defined by the Boolean function f. And this part, so the input set only affect this term. So maybe this term is very important. And okay, so then we now convert the mod to all to the sum of the x to the u by using this method. Okay, so now this is a 4-bit value and mod to all in 4-bit value. So the sum of the x to the 0xf is equal to the number of appearance of the f. So it's a 15, yes. Okay, so now we focus on the number of appearance, x to the 0, the sum of the x to the e. But this is equal to the sum of the number of appearance of E and F. But now this is a mod to all. Odd, odd plus odd is, of course, even. So 0, the sum of the x to the E is 0 mod 2. What? Okay, comes. Okay. And 0xt again is a 0 mod 2. C is a sum of the 4 values, and it's of course mod 2 0. And so I don't need to use this property in the division property, but in fact, this is a 0 mod 4. And mod 2 0, mod 2 0, and mod 4 0, and so on. So as a result, if the set X has a mod to all in 4-bit value, the sum of the X to the U is always equal to 0 for any U is less than 0xf. So by using this view, so that we can distinguish all, and mod to all. So originally this is the all, but so that this is now we want to understand this property. So the sum of the x to the u is equal to 0 for all u is less than 0xff. But mod to all is different. The sum of the x to the u is equal to 0 for u is less than 0x0f or u is less than 0xf0. Otherwise, there is a possibility the sum of the x to the u can be non-zero. So from here, so we can come up with the division property. So the idea is to divide the set of U into two subsets. One is the set of U such that the sum of the x to the U is equal to 0. And another is the set of the U such that the sum of the x to the U is non-zero. So can be independent. So the name of division property comes from this idea. So we have originally the set of U, and we want to divide the set of U into two cases. And also, another important reason is D is missing. So I originally think I always think about the integral property, or property A, balance property B, constant property C, even property E. Okay. Oh, D is missing. So this is the main reason. So that I've actually in there. So I'm looking for the good name from the initial alphabet is D. So I use the D. Okay. So now we want to focus on the low degree function. So of course, I now define the division property, but I need to get some propagations, something. So now, if the degree of the function is D, so what we can say? So now, the sum of the x to the U can be non-zero when the weight of the U is, Hamming weight of the U is larger than K. Then if this function is algebraic degree D, the sum of the y to the U can be non-zero when the weight of U is larger than K over D. So we can prove so by using the conversion of the algebraic normal form, and so that it's possible to prove it. Oh, okay. This idea is very nice because we can successfully handle the low degree function. And of course, so that we need to evaluate the propagations. So this is the idea. So originally we have the division property F0. Then what happens to the S box? But it's S box is a permutation. Then F0. So that after the S box, and in linear layer, so everything is mixed. But the Hamming weight must be preserved. So 12. So the sum of the U1, U2, U3, U4 must be larger than 12. So that if the sum of the x to the U can be non-zero. So for example, we simply assign, okay, 7, 7, 7, 7 is just as example. Then after S box 1, 1, 1, 1, and it's a 7, 1, 0, 0, and there's a 1, 1, 1, 1, 1, 0, 0, but it's a 2. Of course, this is just one trail. So we need to consider all kinds of the trail. And if there is no trail from the beginning to the end, it becomes a unit vector, we can prove the integral distinguishing. Okay, so, okay, I skip this slide. So very sad news for me. So actually, when I developed this tool, up to here, I didn't recognize this paper. I'm sorry, Bora. So, so first I read the papers, I recognize this very nice PCC bands, and I checked my results and I compare the result with SPN cipher, almost the same result. Yeah, so of course the S box, the first layer, so we use S box, we have very slight difference, but almost the same. And actually, the conversion from this bound to the integral cryptanalysis, and it's trivial. So maybe by using this bound, it's possible to get the same result. So, however, I couldn't give up, of course. So I always use the very much time. So almost 1 year or 2 years. I can't give up. But of course, I thought this idea comes from the algebraic degree, but my idea comes from the integral property. So something different. Maybe I can have different result for other kinds of the cipher. So I can focus on the phase there. So it's a non-trivial to apply the degree estimations for the SPN to the FSE. It's a non-trivial, but division property can be possible. And fortunately, so I have a different result. and also the AS. So linear layer is perfectly so the fully mixed. So then there is no difference with BCC bounds. But if we use shift rows and the mixed columns, so the linear layer is different, not the full diffusion one, then we have a different result. Anyway, this is the original question. So initially, this is the question. So now Tsuno's property can't prove this. So the question is, division property prove this property or not? This distinguish or not? So answer is, so we can prove it. So not so good picture. So this is the initial division property with Hamming weight, and there is a trail from this weight is 2. It's possible, and 1 is also possible, but from 1 to here, so there is no trail. So it's impossible to input properties here and output property here, so that's impossible to from here to propagate to here. So we say the sum of the y02 to the u is equal to 0 when the Hamming weight of u is 1. Okay, so in 7 or 8 minutes, I think. So quickly I go. So the story behind breaking Misty 1. Okay, so after proposal of my Eurocrypt paper, so after submitting to the Eurocrypt papers, not before acceptance, I was looking for more attractive target. So originally the division property is applied to the general structure SPN FSE, but so only this maybe not so good. So I think it's maybe I want to break some nice cipher by using these new techniques. And what is target is better. One is low degree S box, because if the degree of the S box is high, integral cryptanalysis, integral property is nice. And another one is a no full diffusion linear layer is good, because if the linear layer is very sort of complicated and mixed everything, then BCC bound is the same. And another is we want to avoid too complicated linear layer. So it's a contradiction to the second condition. So linear layer is simple is better, but too simple is not good, but too complicated is not so good. So something so-so is better. Otherwise, we can't evaluate the propagation in practical time. And famous cipher. It's, of course, very important. And if possible, I want to break the full specification. Okay, so yes, I found nice target. It's a Misty 1. So because Misty 1 has 9-bit S box and 7-bit S box, but this algebraic degree is only 2 or 3. It's too small. Linear layer is complicated. I'm not sure, so it depends on the U. So for me, still possible. And so famous. At least so for Japanese symmetric cryptographic community, super famous. Matsui-san is a hero. So if possible, I want to break the full specification. So now I want to review the previous existing attack against Misty 1. But so I don't want to explain everything because time is limited. But one nice thing is here. So before the division property, we can attack 7 rounds with 5 FL. Full specification is 8 rounds with 5 FL. Security margin is only 1 round. Oh, it's possible. It could be possible. So I just try. So then I've successfully found the new integral distinguishers covering 6 rounds. Original one is only 4 rounds, so that we can improve a 2 round. We can improve the number of rounds of the integral distinguisher by 2 rounds. Okay, so the 2 round improve is enough because 1 round recoveries. It could be possible. So after I found this attack, so I talked with Matsui-san at the Japanese domestic conference. So I say, I break the Misty 1. So he said, oh, which which attack? So I said, so something higher the differential. Okay. So this is just a story that I discussed with Matsuisan. But so after that, after getting the best paper award at Crypto 2050, so I received the one mail from the Matsuisan. So he said, congratulations for breaking my cipher. Congratulations for getting best paper award. I want to get best target award. So this is a Matsuisan said. Okay, so I want to conclude my talk. Sorry, the time is limited. My first step was just experiment. But the division property comes from my ad hoc analysis, and I should have surveyed better. So the one such thing, I should have surveyed existing works seriously in advance. So at least it was heartbreaking to find out later. So it's a bit, in case I can't find any difference with the BCC funds, it's a very sad thing for me. But fortunately, it's no problem. But yeah, so I should have surveyed in advance. But I think maybe it's a good luck, but going on my way might cause a good result. Okay, so thank you very much for listening to my talk. So question.
Well, thank you very much for the very nice talk. So probably we can ask if there are some questions from Beijing first. Then any questions from Kobe?
So thanks for the very interesting and inspiring talk. So because of that, Tsuno-san is my one of my my supervisor. So maybe it's my responsibility to ask something about Tsuno-san. So So did you receive any response from the Tsuno-san in regarding the invention of the division property?
Not yet. Not yet. Yeah, so because I didn't explain it before. So maybe as a link with the Tsuno's property, so that I explained this link here at first time. So maybe Tsuno-san didn't recognize it. And so the very bad thing is, sad, I don't know which wording is better. So I can't cite Tsuno's papers because it's Japanese. So he can't cite the paper I submitting the Euroclip. I can't cite this Japanese papers. So maybe he didn't recognize it.
Yeah. In Japanese community, many researchers are focusing on the integral crypto analysis and trying to break the misty one because as you mentioned, it's a primary target in Japanese community. So it's quite understandable. And maybe I can ask Tsuno-san for something. And he should be very happy to hear your invention and the successful story. Okay, that's fine.
Thank you very much.
Are there any other questions? Kobe or Beijing?
Can I ask one question? So thanks for your interesting talk. Indeed, I always want to know how you invented the division property, and now you give the answers here. So I'm very glad to be here. So one question is that in my imagination, I always thought for your division probability, whether there is indeed some inner structure. For example, you choose a large plain test set. I mean, only one bit is, for example, only one bit is constant, and then you propagate the probability of this set. What I thought is just like the integral attack on 4-round AES. So indeed, the 4-round attack is based on a 3-round attack. So it is in the inner structure in the 3-round attack. So is it possible for your attack? Indeed, there are some similar structure. I mean, for some intermediate round there are only one bit, some constant, and then we propagate backwards. Then we get this set.
So in the context of the integral attack, my view is different. So the original idea is that they first has the inner distinguishes, and it extends to this side. But it means so that in my view, so that now we have the initial structures, and the analysis of this side and this side is independent. But maybe, so I think without analyzing independently, so the analyzing the same together is much better. So my view, and actually when I developed the division property, and the main question is the strange property when we use a higher order integral. And but the higher order integral comes from the inner distinguishes and extend to the predicate side. But if we use it, so we can't observe nice properties, then maybe something nice properties hidden if we consider the top from the top to the bottom at the same time. So I think maybe as analysis from the beginning to the end at the same time is better. So, but this is just my view.
Thank you.
Maybe a very last question, someone? So I have a small question. So if a PhD student now wants to work on the division property, what you suggest him like to look on, what do you think are the challenges that are remain for this kind of attacks? Like more algorithmic aspects, like a look at the milk models, or if there are some mathematical things to do, I don't know.
On the division properties, it's so I think maybe if the student do now, so I think one open question is something a MILP model maybe. So because so the L set, so parity set propagation, so it's not so practical. So it's something feasible, but the application is very limited. And so maybe we need some new techniques or new found, so that if we want to find if we want to get a practical algorithm to evaluate it. So I think this is one good open question.
Thanks. So we can thank again Yosuke for his very nice talk. And can have the coffee break.